The deepest we have ever gazed into the sun. SDO. The sun, our celestial powerhouse, has long captivated the curiosity of scientists and astronomers. Its dazzling light and immense heat have fueled human imagination for centuries. But it is in only recent years that we have managed to delve into its mysteries with unprecedented precision. Among the various missions dedicated to studying it, the Solar Dynamics Observatory (SDO) stands out. This mission allowed us to peer into the sunlit heart of our solar system in ways never before imagined. This is the deepest we have ever seen into the sun. SDO and the solar corona. The sun is like a giant ball of fire in the sky, right? But did you know it has layers like a big burning onion? With its X-ray vision, Solar Dynamics Observatory helps us see through those layers to understand what's happening inside. It was launched by NASA and equipped with advanced instruments and cutting-edge technology. It has been a game-changer in solar observation, revealing intricate details of its complex structure. Firstly, SDO checks out the sun's outer layer called the corona. It's this wild, glowing aura around the sun that you could only usually see with your naked eye during a solar eclipse. The corona is the sun's halo, and it's super hot, even hotter than the sun's surface. Scientists are still figuring out why, and SDO is helping them solve this mystery. X-rays are part of the extreme ultraviolet region of the electromagnetic spectrum. This is the region where SDO looks into. This choice of wavelength is crucial because the corona emits most of its radiation in this range, providing a clearer view of its intricate dynamics. Observations of the solar corona might yield groundbreaking findings in the near future. You see, the sun's surface, or photosphere, has temperatures in the range of thousands of degrees, while the corona, just above it, is inexplicably much hotter, reaching temperatures in the millions of degrees. This stark temperature difference has long puzzled scientists, so much that they call it the coronal heating problem. Despite decades of diligent research and numerous proposed solutions, the so-called coronal heating problem remains an enigmatic frontier in solar physics, waiting to be unveiled by SDO. SDO and solar filaments. But this is not it. Adding to the solar corona, there are gigantic, twisty magnetic threads reaching out from the sun. SDO captured these on camera, and they look like the sun's hair blowing in the solar wind. Sometimes these threads erupt into space, creating dazzling shows called solar storms. But what exactly are they? They stand by the name of solar filaments and are magnificent structures composed of relatively cool and dense plasma suspended in the sun's environment. These can be observed against the solar disk, creating striking visual patterns. What not everybody knows is that the creation of solar filaments is intimately tied to the sun's complex and dynamic magnetic activity. The sun's surface is a bubbling cauldron of magnetic fields, with regions of intense magnetic activity and twisting magnetic loops. When these loops become tangled and stressed, that's when a filament is born. The magnetic field lines act as a scaffolding, holding cool, dense plasma in place, creating the dark thread seen against the solar surface. Solar filaments can take different forms, including quiescent filaments that are stable and long-lasting, and eruptive filaments that undergo sudden and dramatic releases of energy. The latter can lead to solar flares or coronal mass ejections, CMEs, which are powerful and potentially disruptive solar events. Potentially hazardous events that might affect the life on Earth. SDO and the solar transition region. Then there's the transition region, a spacey bridge between the sun's surface and its outer layers. SDO helps us explore this mysterious zone where things start getting crazy hot. It's like the sun's own magic doorway, and SDO is the key to unlocking its secrets. The transition region serves as a delicate and irregular boundary within the sun's atmosphere, acting as the separator between the scorching corona and the considerably cooler chromosphere. In this narrow expanse, heat cascades from the corona to the chromosphere, creating a distinctive layer where temperatures undergo a rapid transformation, plummeting from a searing 1 million degrees Celsius or 1.8 million degrees Fahrenheit to approximately 20,000 degrees Celsius or 40,000 degrees Fahrenheit. At these elevated temperatures, hydrogen undergoes ionization, rendering it challenging to detect. Instead, the emitted light within the transition region predominantly originates from ions such as carbon, oxygen, and silicon, each stripped of 3 electrons. This emitted light falls within the ultraviolet spectrum, accessible only from the vantage point of space. Understanding the Sun's transition region, the delicate interface between the scorching corona and the cooler chromosphere, is a key frontier in solar physics. Why, you may ask? Well, the transition region acts as a conduit for energy transport from the corona to the chromosphere. Investigating the mechanisms behind this process provides fundamental insights into the overall dynamics of the Sun's atmosphere, particularly regarding the enigmatic heating of different layers. Moreover, emitting light primarily in the ultraviolet spectrum, the transition region holds a treasure trove of information about its chemical composition and physical conditions. The Solar Dynamics Observatory, equipped with advanced instruments, plays a pivotal role in capturing and analyzing this ultraviolet emission with unprecedented detail. SDO boasting instruments like the Atmospheric Imaging Assembly (AIA), Extreme Ultraviolet Variability Experiment (EVE), and Helioseismic and Magnetic Imager (HMI) emerges as a cornerstone in the study of the transition region. Its high-resolution imaging, spectral observations, and continuous monitoring capabilities offer a unique vantage point to unravel the dynamic nature of this crucial solar layer. SDO and the Sun's photosphere. Now let's talk about the Sun's visible surface, the photosphere. It's like the Sun's skin, and guess what SDO does? It takes super-duper close-up shots of sunspots, which are like the Sun's freckles but way cooler. These spots are magnets on the Sun, and they can even affect our gadgets on Earth. Thanks to SDO, we know more about these sunspots and how they behave. The photosphere is the Sun's outermost layer visible to the naked eye, a thin sheath where light escapes, radiating into space and bathing our solar system in warmth. This luminous layer is not exclusive to our Sun. Indeed, every star possesses its own unique photosphere, akin to an individualized outer garment that reflects the star's personality and characteristics. Consider the blue brilliance of Sirius, the brightest star in Earth's night sky, signifying a photosphere hotter than our Sun. In contrast, Betelgeuse, a red supergiant, boasts a cooler and redder photosphere, presenting a visual spectacle in the constellation Orion. Each star's photosphere, characterized by its temperature and color, contributes to the diverse cosmic tapestry that adorns our night sky. Understanding the photosphere is paramount to unraveling the Sun's energy generation, magnetic activity, and its influence on the entire solar system. Photons generated within the photosphere embark on an incredible journey. As they escape the Sun, they traverse the vast expanse of space, reaching Earth in a matter of minutes. Yet the photon's origin story is far more intriguing. Born in the Sun's core through processes taking thousands of years, they undergo a randomized journey, bouncing through layers of the Sun before finally emerging from the photosphere. Thus, when we gaze at the Sun, we're not just witnessing the present, but peering into a past marked by millennia of photon meandering. The Sun's photosphere is adorned with a myriad of captivating features, each contributing to its dynamic nature. Sunspots, cooler and darker regions, mark areas of intense magnetic activity. These spots come and go in cycles, influencing the Sun's overall brightness. Granules, like bubbling cauldrons on the Sun's surface, represent convective cells where hot plasma rises, cools, and sinks back into the interior. These granular structures are crucial for understanding the energy transport mechanisms within the photosphere. Magnetic fields play a pivotal role in shaping the photosphere's behavior. Sunspots are often associated with strong magnetic fields, influencing the surrounding plasma and contributing to the ebb and flow of solar activity. Now allow me to show you an incredible video. For 7 days from November 13th to November 19, 2020, SDO's instruments watched as a small sunspot group morphed, merged, and grew into 2 large sunspots, as other sunspots begin to emerge as well. Astronomers selected an image about every 15 minutes, approximately 700 frames, to generate the smooth motion seen in this 26-second movie. The Sun, just like all stars, is made up of hot gases. So hot, in fact, that it's found in the fourth state of matter, the plasma. And like many other stars, these gases are hydrogen and helium in the case of the Sun. Now, the Sun is at its main sequence stage, which means it will continue on fusing hydrogen into helium for another 4.5 billion years. And then it will go into another stage for 1 billion years and become a red giant, burning and fusing helium into a higher element, which is carbon. If you think that the Sun is a piece of work by now, I don't blame you. But wait till you listen to this. The Sun is so full of mysteries and unsolved phenomena. One of these is the Sun's corona. No, not the virus. The Sun's corona is the outermost layer of the Sun's atmosphere. The corona's mystery resides in its temperature. Let me explain. Imagine you're around a source of fire, and as you get closer to the fire, you feel the heat more, and as you move away, you feel the heat less. Well, that's not quite what happens around the Sun. Weird, right? The outermost layer of the Sun's atmosphere, the corona, is actually hotter than the surface of the Sun. The Sun's surface has an overwhelming temperature of 5,726.667 degrees Celsius, 10,340 degrees Fahrenheit, while the atmosphere is well beyond 300 times hotter. The reason behind this abnormal behavior still puzzles scientists till today, but they have a couple of ideas as to why it happens. One of these ideas is what's called nanoflares, presented back in the year 2015. Scientists believe that small explosions called nanoflares burst in the Sun's atmosphere millions of times every second. And even though they are nano in solar terms, they produce an amount of energy equivalent to a 10 megaton hydrogen bomb. These explosions reach a temperature of up to 10 million Kelvin, and they cause the Sun's atmosphere to heat up like we see in the Sun's corona. That's not all that's happening around the Sun. The Sun is very active, and that's not unusual for a star. It has a very strong magnetic field as well. The lines of this magnetic field could sometimes be twisted on and around itself, which helps store a lot of energy that can sometimes suddenly get released. Here's an image showing some active regions of the Sun. The release of that energy is what's called solar flares, and they cover the whole electromagnetic spectrum and are a billion times the energy of the nanoflares we mentioned earlier. Solar flares can be very energetic, and they heat material up to millions of degrees. Scientists classify solar flares into three categories: the X-class flares, which are the major solar flares that produce a huge amount of energy in the X-ray, the M-class flares, which are the medium-sized flares on the X-ray spectrum, and finally the C-class flares, which have the smallest amount of energy. The energy that the solar flares eject are sent through space till they reach Earth, and each class we mentioned have different implications on Earth. X-class flares are the biggest, and they can cause radio blackouts on Earth and around the whole world, as well as interference with radio signals and communications. Solar flares can also mess with electricity lines, causing electricity shortages like what happened back in the year 1859 in London, where a solar flare caused telegraph lines to stop and burnt telegraph paper. This incident is better known as the Carrington event, and probably one of the biggest outcomes of solar flares in modern history here on Earth happened back on March 13, 1989 in Quebec, Canada, when the whole province suffered from an electrical blackout of power grids that lasted as long as 12 hours. The blackout was traced back to an explosion astronomers had observed 3 days earlier on March 10th on the surface of the Sun. Following the explosion was a release of energy, the equivalent of 1,000 nuclear bombs, which was traveling back to Earth at 1,000,000 miles per hour. The same solar flare also jammed radio communications, and didn't only affect Canada, but had its consequences on power grids in the United States as well. New York Power lost 150 megawatts of energy, and New England Power lost 1,400 megawatts of energy, causing 200 power grid problems across the United States within minutes of the star's solar storm. M-class flares, on the other hand, can cause brief blackouts only in the polar regions of Earth, while C-class flares are usually unnoticeable to Earth. Scientists say that solar storms causing major blackouts, like what happened in Quebec, are rare, but scientists also confess it's actually a matter of chance and can't be exactly known which solar flare will cause blackouts. So due to all these unfortunate implications of solar flares and solar activities, it is crucial for astronomers to keep on studying the sun and understanding more about the solar activities in order for them to better predict the sun's space weather, because better predictions will ultimately lead us to come up with better solutions to avert the problems caused by solar flares, because nobody would like to lose electricity and internet access for 12 hours in the future. However, solar flares' effects are not all bad and harmful to Earth. In fact, they're actually indirectly responsible for some of the most wonderful scenes on Earth. I'm talking about the auroras. Solar flares can produce what's called coronal mass ejections, or CME, which are a combination of radiation and particles that interact with gases in Earth's atmosphere and excites them to a higher state. And when the gases fall back into their normal state, they produce energy in the form of the magnificent northern and southern polar lights, the auroras. And if you're wondering about the different colors of the aurora, that's due to different gases in Earth's atmosphere. When the CMEs interact with the oxygen in Earth's atmosphere, they produce a greenish yellow light or a red light. And when the CMEs interact with nitrogen in Earth's atmosphere, they produce a blue light. We hear a lot of myths about the sun disappearing or the sun engulfing the Earth. But is there any truth to that? Well, as we established before, the sun still has 4.5 billion years burning hydrogen into helium. So none of us should worry about any mysterious disappearances from the sun. But I hope you like thought experiments, because we are going to imagine the most extraordinary event that could ever happen to our sun. What if the sun got sliced up? This is a pretty wild thought, but let us indulge in it and see how it's going to turn out. The first step is obtaining the right tools. You can't simply take out the table knife and travel to space to slice up the sun. We would need an extremely sharp tool made out of a material that is ridiculously heat resistant to sustain the enormous temperature of the sun at 27 million degrees Fahrenheit or 15 million degrees Celsius. First, I need to warn you that such a tool doesn't exist, because there simply isn't a material right now that would not melt under such temperatures. But that's why this is only a thought experiment. You gotta be a little imaginative. The second tool you're going to need is also as challenging as the first, which is a custom-made spacecraft to travel up to the sun and also withstand the temperature to perform the slicing. We can't send a human for obvious reasons. Ready with the two impossibly obtained tools? Let's find out what happens after you slice open the sun. There are 4 major consequences to slicing only a quarter of the sun, moving down through all its layers till we reach the core. The first, harmful radiation. On Earth, we first will have to deal with gamma radiation bursting towards us. That's because the solar core is now exposed with no solar atmosphere to filter out harmful radiation from the sun's core. The second, deadly cold. The gamma ray radiation that will rush towards Earth will also lead it to its eternal winter, because the radiation will break the bonds between oxygen atoms and nitrogen atoms in Earth's atmosphere that keep the planet warm, as well as nitric acid rain pouring down on Earth. The third, the birth of a new sun. You might think that a quarter is not a huge portion, but in solar terms, this is a pretty enormous chunk of the sun. And after losing all that mass, the sun will never be the same, and it will be quite unpredictable with an increase of solar activity because the sun will be in a stage of rebirth. The fourth, solar system disruption. The sun accounts for 99.8% of the solar system. It keeps all the planets, dwarf planets, asteroids, and other objects in a precise orbit and a perfect harmony between each other. When a quarter of the mass of the sun is sliced, we are looking into a hectic solar system with different orbits and probably massive collisions between planets and other extraterrestrial bodies in the solar system. The Earth may not even still be in orbit around the sun, but wander off in the vast darkness of space. On March 13, 1989, planet Earth was attacked from space. A catastrophic event occurred that left millions of people without power and resulted in extensive damage. While one might assume that this was the result of an unnoticed alien attack, the truth is far more plausible: a solar storm. The effects of this solar storm were particularly devastating in Quebec, where an estimated 6 million people were left powerless. Imagine waking up to a cold home, businesses and schools shuttered, and even the bustling Montreal Metro having to halt its operations during morning rush hour. To make matters worse, the airport was also forced to close its doors. The impact was truly immense. This solar storm unfolded during a period known as Solar Cycle 22, characterized by heightened solar activity. These cycles occur approximately every 11 years, and scientists predict that a similar event to what transpired in Quebec could potentially happen again. But don't worry, as you will see at the end of this video, every medal has two sides. The importance of the Sun. In the grand tapestry of the cosmos, the Sun holds an unparalleled significance for our planet Earth. It stands as the radiant centerpiece, the beacon of life, and the architect of Earth's rhythms. Its influence transcends the boundaries of the celestial realm, permeating every facet of our existence. In this video, we shall embark on a journey to uncover the profound importance of the Sun, delving into its multifaceted roles that shape the very existence of life on our blue-green orb. At the heart of the Sun's paramount importance is its role as the ultimate source of energy for life on Earth. Through the process of nuclear fusion, the Sun emits a ceaseless torrent of light and heat, illuminating the cosmos and bathing our planet in life-sustaining radiation. This energy is harnessed by Earth's biosphere, initiating a cascade of processes that drive photosynthesis, the bedrock of terrestrial life. Photosynthesis, orchestrated by an intricate array of plant life, transforms sunlight into chemical energy, breathing life into Earth's ecosystems. It is this process that endows our planet with the oxygen we breathe and the sustenance we consume. In essence, the Sun is the cosmic engine that fuels the cycle of life on Earth, supporting an intricate web of interdependent organisms. Beyond its role as an energy bestower, the Sun is Earth's master orchestrator, weaving the fabric of climates and seasons. Its rays, striking at various angles throughout the year, govern the ebb and flow of temperature and weather patterns. The tilt of Earth's axis relative to its orbit around the Sun bequeaths us with the symphony of seasons: spring's awakening, summer's warmth, autumn's harvest, and winter's reprieve. These seasonal shifts sculpt the landscapes and habitats that cradle life. They dictate the migratory patterns of countless species, influence the behavior of flora and fauna, and guide the life cycles of numerous organisms. Moreover, the Sun's radiant energy drives the water cycle, a fundamental force that sustains the delicate balance of Earth's ecosystems. The Sun is ever-changing. The photosphere, the visible surface of the Sun, serves as our gateway to the wonders of our star. It is through this unique window that photons generated in the Sun's core escape and journey across the universe, ultimately reaching our eyes. These particles of light, which have traversed the depths of space for longer than we can comprehend, greet us whenever we gaze upon the Sun. The photosphere, therefore, is not merely a part of the Sun, but a conduit that connects us to its majesty. However, accessing the photosphere was not always feasible for early astronomers. Their rudimentary telescopes, ill-equipped for studying the Sun's astrophysics, were hindered by their blinding brilliance. Attempting to observe the Sun directly would have resulted in irreparable damage to their eyes. Yet as time passed, astronomers discovered a solution: specialized filters that enhance the observability of the Sun. Through these filters, they were able to discern the presence of granules on the photosphere, resembling a pot of boiling water dotted with tiny, moving bubbles. Astonishingly, each of these granules measure about 1,000 kilometers wide, dwarfing our own planet. Intriguingly, these luminous granules were often accompanied by a contrasting phenomenon known as sunspots. These dark spots emerge due to the influence of powerful magnets beneath the Sun's surface. They appear cooler and darker compared to their surroundings, drawing the attention of astronomers. Like clockwork, the cycle of bright granules gives way to the enigmatic appearance of sunspots. In a nutshell, sunspots form when magnetic field lines below the surface poke through the Sun's photosphere. Occasionally, the Sun, perhaps feeling particularly exuberant, treats us to extraordinary displays of solar flares and prominences. Solar flares akin to splendid fireworks composed of minuscule particles embellish the Sun with vibrant hues, emitting a special form of light. Prominences, on the other hand, manifest as mesmerizing loops of fire that elegantly dance above the Sun's surface, reminiscent of a celestial crown adorning our star. And then there are faculae, the radiant patches that punctuate the photosphere. These areas, characterized by intense magnetic activity, emit a brilliant glow that distinguishes them from the rest of the sun's surface. Indeed, the photosphere is a bustling stage, teeming with movement and captivating surprises. It is here that the sun orchestrates a grand performance for us, a spectacle that reminds us of its boundless wonders and tantalizing mysteries. However, if you happen to point your telescope at the sun at random times, you might not be able to see anything. In other words, there are periods where the sun's photosphere is almost devoid of any feature, and others where it is enriched with them. Astronomers long wondered and studied this phenomenon, and they have come to the conclusion that the sun undergoes cycles. Solar minimum and maximum. Indeed, our radiant celestial neighbor is far from static. For example, sunspots wax and wane every now and then, and so does the magnetic field by literally flipping its orientation over the course of 22 years. The first cycle regarding the sunspots is the Schwabe cycle, named after the Swiss astronomer Samuel Heinrich Schwabe. It spans approximately 11 years, and it is characterized by the waxing and waning of sunspots on the sun's surface. At the cycle's maximum, sunspots are abundant, creating dark spots on the sun. As the cycle progresses to its minimum, sunspots become less frequent. Schwabe cycles are repetitive yet difficult to predict. A cycle can be as short as 8 years or as long as 14 years and varies dramatically in intensity. The current cycle, solar cycle 25, began in December of 2019. Solar activity is expected to ramp up until the predicted solar maximum. The second cycle, on the other hand, is known as the Hale cycle, and it takes twice as long as the Schwabe cycle to occur. What makes the Hale cycle particularly intriguing is its focus on magnetic polarity. Over the course of this cycle, the sun's magnetic field flips, the north magnetic pole becoming the south magnetic pole and vice versa. Picture this. At the beginning of a Hale cycle, the magnetic field lines emerge from the sun's northern hemisphere. By the cycle's end, they reverse, emanating from the southern hemisphere. In other words, the Hale cycle is made up of two Schwabe cycles with two different polarizations. The polarization reversal is a very common process in the universe. Earth's magnetic poles also flip, but the interval between the reversals is much longer, averaging about every 300,000. The last pole reversal happened about 780,000 years ago. Last but not least, the Gliesberg cycle is a more extended cycle, with a period of about 88 years that concerns the amplitude of the sunspot activity over time. While not as pronounced as the Schwabe or Hale cycles, the Gliesberg cycle hints at more complex long-term variations in solar activity. Researchers believe that this cycle may be influenced by interactions within the sun's interior, but research is still ongoing. Solar cycle driver. Out of all the cycles that have been studied, the Schwabe cycle stands out as the most fundamental and captivating. It raises some important questions that have led researchers to delve deeper into the forces that drive it and the reason behind its 11-year duration. To comprehend what propels this cycle, it is crucial to understand the definition and origins of it. The first person to provide a definition for this cycle was Schwabe himself. He meticulously observed the sun from 1826 to 1843 and made a groundbreaking discovery. The sun rotates on its axis once every 27 days. Furthermore, he discerned that the sun's activity experiences a cyclic pattern over the course of approximately 11 years. Schwabe's theory was primarily based on the emergence and disappearance of sunspots, which are known to be created by the sun's magnetic field. Consequently, it can be understood that the primary driving force of the Schwabe cycle is indeed the sun's magnetic field. The cycle experiences a period of rise from minimum to maximum phase, which typically spans around 4 years, followed by a subsequent decrease from maximum back to the minimum that spans approximately 7 years. Another significant observation made by Schwabe was that the sun's activity has a direct impact on Earth. The solar cycle induces variations in our planet's magnetic field. During the solar maximum, characterized by an abundance of sunspots, solar flares and coronal mass ejections, CMEs, explosive releases of charged particles from the sun's surface, terrestrial effects become more pronounced. An event of this nature occurred on March 13, 1989, when a colossal CME caused a major blackout in Quebec. This incident highlighted the profound influence of energetic particles carried by the solar wind on our weather patterns and the potential for disruption to communication, navigation, and power systems. Presently, it appears that we are on the brink of a new solar maximum. This implies that we can expect a surge in sunspot activity, an abundance of coronal mass ejections, and an overall increase in the sun's unpredictability. While this may be exciting for scientists studying the sun, it poses a significant risk to our satellites and telecommunication systems, which could be compromised by the intense and unpredictable solar activity. This could start soon. Consequences. First of all, it could interfere with your mobile devices. Perhaps you won't be able to use your phone for a whole day. Perhaps that will be an occasion for us to gather and experience how life was before the advent of social media. But how does this work exactly? Well, during a solar storm, the Earth's magnetic field is disturbed by a surge of charged particles from the sun. This can induce electrical currents in conducive systems on Earth, including power lines, pipelines, and even long metallic structures like railways. Mobile phones, especially those in areas with weaker signal strength or in regions close to power lines, may experience interference or disruption in service. This interference can manifest as dropped calls, static on the line, or even difficulty in establishing connections. Additionally, electronic circuits in mobile phones can be affected by the increased level of electromagnetic radiation during a solar storm. This might result in temporary malfunctions or reduced performance. But every medal has two sides. Hear me out. There will be no better time for you to experience amazing auroras during the solar maximum. Why, do you ask? Well, this is quite easy to explain. Auroras occur when charged particles from the sun collide with gases in Earth's atmosphere, such as nitrogen and oxygen. These collisions release energy in the form of colorful light. During a strong solar storm, auroras can be visible at lower latitudes than usual, sometimes even in regions where they are not typically seen. This means that people at lower latitudes who don't often get the chance to witness auroras may have the rare opportunity to see these beautiful natural displays. Why does the Earth orbit around the sun? Since the dawn of time, humans have pondered the question, why does the Earth revolve around the sun? The answer lies in the powerful force of gravity, which binds the sun and the planets together in our solar system. The Earth is held in orbit by the sun's gravity. The sun's gravitational force is strongest at its center. Therefore, planets that are closest to the sun will be pulled in tighter. As far as we know, this dance will last up until the sun dies. Nowadays, it's not hard for us to believe in such things. Everything seems quite normal and trivial to us. But if we go back, we soon realize how difficult it for humankind was to reach this self-consciousness level. Back then, scientific concepts weren't as trivial as you think. Keep watching the video to get to know more about the forces that keep the Earth, the Moon, and other planets around the Sun. Spoiler alert, the same laws apply to exoplanets and exomoons. Historical context. The concept of heliocentrism, that is, the idea that the Earth revolves around the Sun and not the other way around, has been around since the time of the ancient Greeks. The ancient Greeks believed in a geocentric universe, where the Earth was at the center of the universe and was the stationary point around which all the planets and stars revolved. It was not until the time of Nicholas Copernicus, however, that heliocentrism began to gain traction. Copernicus was an astronomer and mathematician who published a book in 1543 called On the Revolutions of the Celestial Spheres, outlining his heliocentric model of the universe. His model attempted to explain the observed motion of the planets by postulating that the planets rotate around the Sun and do not revolve around the Earth. In addition to Copernicus, two other influential figures in the development of heliocentrism were Galileo Galilei and Johannes Kepler. Galileo studied Copernicus's model and was one of the first to observe that Venus went through phases like the Moon, which confirmed the heliocentric model. He also observed the moons of Jupiter and used the idea of heliocentrism to explain them. Kepler was a mathematician and astronomer who discovered the three laws of planetary motion, which described the motion of planets around the Sun in mathematically precise terms. The concept of heliocentrism was met with much resistance from the Church, which held to the geocentric view of the universe. This eventually led to Galileo's trial for heresy and ultimately to the acceptance of the heliocentric view of the universe. Today, heliocentrism is accepted as a scientific fact, and we have sophisticated tools like telescopes and satellites to observe planets and stars more accurately, allowing us to further understand the heliocentric model and its implications. Observational evidence. The evidence for heliocentrism became stronger when Johannes Kepler, a German astronomer, noticed that the orbits of planets around the Sun were elliptical. His contribution to the scientific world has been immense. He was the first to propose that galaxies were composed of stars, and that stars moved in patterns. His work on the nature of light and the laws of geometry are still used today. He also developed the first modern telescope. But what really throws some astronomers for a loop is Kepler's 3 laws of planetary motion. The first law: every planet orbits the Sun in an ellipse, with the Sun at one of 2 foci. This one is so predictable that it's almost boring. The second law: a line between the Sun and a planet sweeps out equal areas at equal times. This one is a little more interesting. The faster a planet is moving, the further away from the Sun it gets. That's why the solar system's outer planets take longer to orbit than its inner planets. The third law: the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This one is the most interesting because it allows astronomers to predict the orbits of planets, moons, and asteroids. But here's the thing. Kepler's third law is sometimes referred to as Kepler's fun law. This is because astronomers often play a game called Kepler's fun. The object of the game is to use the equation to calculate how long it would take a planet to orbit the Sun if it were twice as far away. It's a great way to pass the time and a useful tool for teaching kids about the universe. For those looking for more than just a game, Kepler's laws can provide useful insights into the nature of the universe and how it works. But for now, let's just enjoy the game of Kepler's fun. It's a great way to explore the solar system and have fun doing it. Perhaps the observational evidence that contributed the most to the fall of geocentrism came from Galileo Galilei. The famous scientist and professor conducted several experiments in 1609 and 1610 to observe the moons of Jupiter and proved that the Earth was not the only body revolving around a bigger object. His observation demonstrated that the planets revolve around the Sun, and from this evidence, he concluded that the Sun, not the Earth, was the center of the solar system. This observation by Galileo helped to solidify the heliocentric model of the solar system. It also demonstrated that the universe was more complex and that our understanding of it needed to be updated to include heliocentrism. So we know that the planet Earth revolves around the Sun, as well as all the other planets in the solar system. But will it ever stop doing so? Stability of the orbits. The revolving of the Earth and other planets around the Sun keeps the solar system in a stable state. Without the Earth's orbit, life as we know it would not exist. It is the gravitational pull of the Sun that helps keep the planets in their orbits, providing us with the warmth and light necessary for life. As long as the Sun remains active, it is highly unlikely that the Earth and other planets will ever stop orbiting around it. The Sun has been around for 4.5 billion years and is expected to remain in its current state for at least another 5 billion years, so the planets will continue to rotate around the Sun for a very long time. The orbits of the planets do not remain the same over time, however. Although the orbits remain stable, they can drift slowly over time due to gravitational influences from other objects in the solar system. The most notable example is the eccentricity of Mercury's orbit, which slowly increases over centuries due to the gravitational pull of other planets. There are also external forces that can alter the orbits of the planets. In some cases, asteroids or comets can pass close enough to the planet to alter its orbit. Even the slightest change to an orbit can have drastic consequences, such as a planet drifting away from the Sun or crashing into another planet. In conclusion, although the orbit of a planet can change over time, it will remain in a stable state as long as the Sun remains active. Exoplanets and exomoons. But what about exoplanetary systems and exomoons? Even though they are much further away from us, they still follow the same laws of physics and orbital dynamics. This means that many of the principles that we understand to be true for our solar system also apply to exoplanetary systems. In particular, exoplanetary systems exhibit the same stability as the solar system. Like the Earth, exoplanets are held in orbit by the gravity of their sun. This powerful force binds the exoplanetary system together and keeps the planets in a stable state, preventing them from drifting away or crashing into each other. The same laws of physics that govern the behavior of the planets in our solar system help to keep the exoplanets in orbit, providing the same level of stability for those distant universes. The eccentricity of exoplanetary orbits may also be affected by interactions with other objects in the system. This can cause the orbits of exoplanets to drift over time, like the orbit of Mercury in our solar system. The external forces of passing asteroids or comets can also potentially alter the orbits of exoplanets, although this is much less likely as they are much further away from the Sun. We don't really know much about exomoons because we never really observed one. Nevertheless, we are sure they exist. I mean, they must exist. It would be really weird if they didn't. Finding an exomoon is another level of difficulty. They are even smaller and harder to detect than exoplanets. It would be similar to trying to detect a tiny grain of sand near a headlight miles away. Nevertheless, Columbia University astronomers may have detected the first ever exomoon. Alex Tichy and David Kipping combed through Kepler data for hundreds of exoplanet detections, and one record stuck out. The data indicated that the star Kepler 1625, 8,000 light-years away, had dimmed once from Kepler 1625b, a Jupiter-sized planet passing by, suggesting the presence of an exoplanet. But curiously, it had also dimmed again within a day for a similar amount of time. It couldn't be the same planet. There wouldn't have been enough time for the planet to loop around in a matter of hours, because a single orbit should be around 287 days. And it probably wasn't a second planet because another planet traveling at the same speed as Kepler 1625b would share its orbit and likely collide with it, while a planet in a different orbit would travel faster or slower than Kepler 1625b. Then finally, could this be an object trailing just behind the planet? Maybe this was an exomoon. This video, published by ESA, shows what they actually saw. This might be the first convincing evidence for an exomoon. In conclusion, the stability of exoplanetary systems is largely reliant on the same forces that keep our solar system in equilibrium. This is the strength of physics. Provided the conditions are the same, the laws stay the same everywhere in the universe. The power of the star's gravity controls the orbit of the exoplanets, providing stability to their systems. Although the orbits may drift over time, the same laws of physics apply, ensuring that the exoplanets remain in a stable state for a very long time. It is an incredible thought to realize that the Earth's orbit and the Sun's gravity combine to keep us safe and secure in our own solar system. So the next time you look up in the sky, remember that it is the Sun's force of gravity that is keeping the Earth in its orbit, allowing us to exist and thrive. Journey to the future of the solar system and the destruction of the Sun. In the coming billions of years, our Sun will undergo a series of transformations destined to completely change the characteristics of every body in the solar system. The star that peacefully illuminates Earth today will first become a planet-devouring red giant, then a small white dwarf that will cool for hundreds of billions of years. The evolution of a star represents one of the most complex physical processes in the universe, governed by delicate balances between nuclear fusion, gravitational pressure, mass loss, and magnetic interactions. Every planet, moon, and minor body will experience dramatic changes, not only in surface conditions but also in orbital dynamics, atmospheric composition, and fundamental physical characteristics. This cosmic chronicle, based on the most recent computational models of stellar evolution and observations of planetary systems in various evolutionary phases, reveals a destiny as complex as it is inevitable for every world in our system. This spectacular journey will take you from today to the end of time, and after watching it, you too will never be the same again. The Sun today. A nuclear reactor slowly transforming itself. If we could peek into the heart of our Sun right now, we'd witness an incredible spectacle. The stellar core is operating like a gigantic nuclear reactor at 15.7 million Kelvin or 28 million degrees Fahrenheit. With a density of 150 grams per cubic centimeter, 150 times that of water, converting 4.3 million tons of matter into energy every second through the proton-proton reaction. It's a cosmic furnace that burns hydrogen, transforming it into helium and releasing energy so immense that it reaches us after an 8-minute journey through space. What might seem like a stable process actually hides gradual yet inexorable changes. Every passing year, our Sun loses 140 billion tons of mass through radiation and solar wind. That might sound like a lot, but for a star, it's like losing a grain of sand. However, this seemingly insignificant process has a curious effect. It causes all planets to gradually move away from the Sun, with their orbits expanding by about 1.5 centimeters per year. Imagine, while you're reading this article, Earth is slowly moving away from the Sun. It's the conservation of angular momentum that ensures this phenomena. As the Sun loses mass, all planets gradually move away, with their orbits expanding proportionally to the stellar mass loss. 1.5 billion years. The beginning of the end. Let's now take a leap into the future of 1 to 2 billion years. Our descendants, assuming they still exist, will face a climate problem of unimaginable proportions. The Sun's brightness will increase by 15 to 20%. That might not sound like much, but the consequences will be devastating. Earth's average temperature will rise from 59 degrees Fahrenheit to 95 to 104 degrees Fahrenheit, 15 to 40 degrees Celsius, exceeding the critical threshold for runaway greenhouse effect. Water vapor is a powerful greenhouse gas, so the more water evaporates, the more Earth heats up, the more water evaporates. It's a self-feeding process that will bring about the end of Earth as we know it. Meanwhile, our planetary neighbors will experience equally dramatic transformations. Mercury, already the hottest planet in the solar system, will experience extreme heating. The dayside temperature will rise from 800 degrees Fahrenheit to over 932 degrees Fahrenheit, 427 degrees to 500 degrees Celsius, while the night side remains frozen at minus 279 degrees Fahrenheit or minus 173 degrees Celsius. Those small water ice deposits hidden in permanently shadowed polar craters will begin accelerated sublimation, forever eliminating the vast reserves of volatile materials on the innermost planet. Venus, which already lives in runaway greenhouse conditions with a surface temperature of 864 degrees Fahrenheit or 462 degrees Celsius, will become even more hellish. Its dense CO2 atmosphere will become even more turbulent, with surface winds increasing from 2.2 miles per hour to over 11 miles per hour, or 1 to 5 meters per second. That might not sound like much, but imagine 11 mile-per-hour winds in such a dense atmosphere. But there's interesting news. Mars will enter a temporary climate renaissance phase. The red planet, cold and desolate today, will see its average temperature rise from minus 81 degrees Fahrenheit to minus 49 degrees Fahrenheit, or minus 63 to minus 45 degrees Celsius. This will trigger partial sublimation of the polar caps, and water vapor content in the Martian atmosphere will increase, creating clouds and possible precipitation in equatorial regions. For the first time in billions of years, it might rain on Mars. 2.5 billion years. Farewell to Earth's oceans. Moving forward in our time journey to 2.5 billion years in the future, the Sun will have reached 1.3 times its current brightness, and Earth will experience catastrophic greenhouse conditions with surface temperatures of 140 to 176 degrees Fahrenheit or 60 to 80 degrees Celsius. The oceans that once covered 71% of Earth's surface will be in accelerated evaporation phase. What happens next is a process of terrible beauty. Water vapor will reach the stratosphere, where, under the action of UV radiation intensified by the hotter sun, dissociates into hydrogen and oxygen. Hydrogen, being extremely light, will begin escaping to space at a dizzying rate. In just 500 million years, Earth will lose the equivalent of an entire ocean. The released oxygen instead will react with surface rocks, forming oxides and causing global reddening of the terrestrial landscape. Earth, once blue, will become a red planet. Meanwhile, Mars, now with an average temperature of minus 31 degrees Fahrenheit or minus 35 degrees Celsius, will experience more positive moments. The planet will experience partial permafrost thawing and formation of temporary lakes and equatorial depressions. Imagine, after billions of years of aridity, Mars will have liquid water on its surface again. 3.5 billion years. Mars becomes home. Here we arrive at one of the most fascinating chapters of this cosmic chronicle. Between 3 and 4 billion years from now, when the Sun reaches 1.4 to 1.6 times current brightness, Mars will enter its first temperate climate phase with average temperatures of 59 degrees Fahrenheit or 15 degrees Celsius at mid-latitudes, and up to 86 degrees Fahrenheit or 30 degrees Celsius in equatorial regions during summer. Think about it. Mars will become warmer than many European cities in winter. The Martian polar caps will retreat significantly, releasing enormous amounts of CO2 trapped in ice and thickening the atmosphere to 15 to 20 millibars, double current pressure. This would represent the optimal time for human migration to Mars, assuming our species is still around. The Martian environment of that period, while still requiring pressurized life support, would be incredibly more hospitable than current conditions. Tolerable temperatures for humans, water availability from melting permafrost, and a denser atmosphere that would greatly facilitate spacecraft landings and propellant production from atmospheric CO2. But beware, this Martian habitability window will have a limited duration of about 500 million years. That's a very long time by human standards, but a blink of an eye on cosmic scales. The absence of a global magnetic field will allow the solar wind, now intensified by a factor of 2 to 3, to progressively erode the thickened atmosphere. It's like having a boiling pot without a lid. The contents gradually evaporate. So anyone planning a long-term survival strategy should already think about the next destination. During the final centuries of Martian habitability, future humanity will need to prepare migration toward the outer solar system, with Titan as the primary destination and Triton as a long-term backup plan. 4.5 billion years. Inner planets become uninhabitable. Let's now move to an even more remote future. Between 4 and 5 billion years from now, Earth will have completely lost its oceans and most of its atmosphere. Surface temperatures steadily above 212 degrees Fahrenheit or 100 degrees Celsius will make survival of any life form we know impossible. Our home planet will have become a desolate and arid world. Mars will also begin its transition towards a desert world, very different from what we know today. The atmosphere, continuously eroded by intensified solar wind, will gradually thin, but increasing solar brightness will maintain elevated temperatures. Average temperature will stabilize around 68 to 86 degrees Fahrenheit, or 20 to 30 degrees Celsius, transforming Mars into a hot desert similar to Earth's most arid regions today. No longer the cold red planet we know, but a hot and arid world. However, while inner planets experience these climate dramas, outer planets will finally begin experiencing significant changes. Europa, Jupiter's icy moon, will go from minus 256 degrees Fahrenheit to minus 184 degrees Fahrenheit, minus 160 to minus 120 degrees Celsius, causing greater activity in the subsurface ocean hidden beneath its ice crust. It's the beginning of a story that will become very interesting for us in the subsequent billions of years. Hey guys, just a moment before we continue. Don't forget to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. 5.4 billion years. The Sun begins to die. We now arrive at the moment that will change everything. 5.4 billion years from now, nuclear fuel in the Sun's heart will be completely exhausted. It's as if the cosmic furnace that has powered the solar system for over 10 billion years has run out of fuel. The core, now composed of pure helium, will begin contracting under its own gravitational weight. What happens next is a fascinating process. Nuclear temperature will skyrocket from 28 million degrees Fahrenheit to 90 million degrees Fahrenheit, 15.7 to 50 million Kelvin, while density increases by a factor of 10. The result? Solar brightness will rapidly increase from 1.65 to 3.5 times current levels in just 100 million years. Effects on planets will be dramatic and immediate, as if someone had suddenly cranked up the cosmic thermostat. Mercury will live its final moments. Daytime temperature will reach 1472 degrees Fahrenheit or 800 degrees Celsius, causing vaporization of the last traces of volatile materials. The surface will begin a vitrification process, forming vast plains of molten silicates. Imagine a landscape of molten glass that solidifies and melts in a continuous cycle. Venus will become even more hellish. The already dense atmosphere will heat further, with surface temperature rising to 1,112 degrees Fahrenheit or 600 degrees Celsius. Surface winds will dramatically accelerate to 45 to 67 miles per hour or 20 to 30 meters per second. It's like a perpetual fire hurricane. Earth will enter its final phase as a habitable planet, becoming a sort of extreme Venus. Surface temperature will reach 302 to 392 degrees Fahrenheit or 150 to 200 degrees Celsius, while atmospheric remnants, now dominated by water vapor and CO2, will reach pressures of 5 to 10 bar or 5 to 10 times current Earth pressure. Surface rocks will begin thermal metamorphism processes on a global scale. It's as if the entire planet were put in a giant oven. Mars will experience one last dramatic climate convulsion. Equatorial temperature will temporarily reach 104 degrees Fahrenheit or 40 degrees Celsius, causing massive polar cap sublimation. It will be the last time Mars has a relatively thick atmosphere, albeit only for a few million years. 6.2 billion years, the Sun becomes an orange star. The Sun will officially enter what astronomers call the subgiant phase, characterized by rapid and dramatic changes. Its diameter will double while surface temperature decreases from 10,436 degrees Fahrenheit to 8,940 degrees Fahrenheit, or 5,780 to 5,200 Kelvin, giving the Sun a distinctly orange color. Brightness will exponentially increase from 3.5 to 8.5 times current solar levels. The solar wind will dramatically intensify, with particle density increased by a factor of 5 to 10. For the first time in solar system history, outer planets will begin experiencing significant climate changes. It's as if the solar system's habitable zone is expanding outward. Europa, Jupiter's icy moon, will see its first partial global thaw. Temperature will rise from minus 256 degrees Fahrenheit to minus 130 degrees Fahrenheit, or minus 160 to minus 90 degrees Celsius, causing active surface ice sublimation. But the most interesting thing will happen in its hidden ocean. The subsurface ocean will warm from 27 degrees Fahrenheit to 36 degrees Fahrenheit, minus 3 to plus 2 degrees Celsius, intensifying hydrothermal activity on the ocean floor. It's possible that life forms that evolved in that dark ocean will experience unprecedented prosperity. Io, Jupiter's volcanic moon, will become even more active. Total power dissipated by volcanoes will fuel sulfur plumes reaching heights of 500 kilometers, almost double current ones. Titan, Saturn's fascinating moon, will begin its transformation. Surface temperature will rise from minus 292 degrees Fahrenheit to minus 238 degrees Fahrenheit, or minus 180 to minus 150 degrees Celsius. Methane lake evaporation will accelerate, thickening the atmosphere. Even for Saturn's massive moon, this is the beginning of a story that will become very important for us in the next billion years. 7 billion years, the red giant era. Prepare for the most dramatic chapter of this cosmic chronicle. The Sun will begin its most spectacular transformation, rapidly expanding to become 15 to 30 times larger than today. Brightness will reach 150 to 300 times current levels, while surface temperature drops to 7,232 degrees Fahrenheit or 4,000 degrees Celsius, transforming our star from yellow to an intense red giant that would dominate the sky of any surviving world. But there's something even more interesting. For the first time since stellar evolution began, orbital changes will become significant. Solar mass loss, now accelerated to an incredible rate, will cause substantial orbital expansion. Mercury will move from 0.39 to 0.52 AU, or 36 to 48 million miles. Venus from 0.72 to 0.95 AU, or 67 to 88 million miles. Earth from 1.0 to 1.33 AU, 93 to 124 million miles. It's as if all the planets are being pushed farther from the Sun that's losing its gravitational grip. Mercury, farewell forever. Unfortunately for Mercury, this retreat won't be enough to save it. Mercury will be the first planet to experience total destruction. When the Sun reaches 50 solar radii, about 0.23 AU, its extended atmosphere will completely engulf the innermost planet. Temperature in that part of the solar atmosphere will reach 4,500 degrees Fahrenheit or 2,500 degrees Celsius, instantly vaporizing Mercury's surface. The destruction process will be both terrifying and spectacular. The rocky surface will transform first into lava, then into silicate vapor at 5,400 degrees Fahrenheit or 3,000 degrees Celsius. The heavier compounds of Mercury's core, iron and nickel, will resist longer, forming a tail of metallic vapors extending millions of kilometers behind what was once the planet's orbit. It'll be like seeing a gigantic comet made of vaporized metal. Venus, an uncertain but probably tragic fate. The fate of Venus remains one of the most debated and fascinating aspects of future solar evolution. When the Sun reaches 100 solar radii or 0.47 AU, Venus will find itself right at the edge of the extended solar atmosphere. According to scientists, the most likely scenario will be Venus gradually engulfed by the solar atmosphere. The dense Venusian atmosphere, which might initially protect it, will eventually cause atmospheric friction that gradually slows the planet, making it spiral inexorably toward the solar core. The death process would require 10 to 50 million years, during which Venus would transform into a giant comet with a spectacular tail of atmospheric vapors. Imagine an entire planet becoming a comet. Earth, suspended between life and death. Our home planet will find itself in the most precarious position of all. The most recent 2008 studies suggest Earth will probably be swallowed due to tidal interactions with the weakly bound stellar envelope of the red giant sun. Earth's fate will depend on the precise balance between orbital expansion due to solar mass loss and friction caused by the extended stellar atmosphere. If Earth miraculously survives, it would emerge as a completely unrecognizable world. Completely remelted surface, vaporized atmosphere, oceans evaporated billions of years ago. The new Earth would be a sphere of vitrified rock with diameter reduced by 5 to 10% due to loss of volatile materials. No longer the blue planet we know, but a sphere of cosmic glass. Mars, the incredible rebirth of the red planet. But here's the most extraordinary surprise of this entire chronicle. Mars will enter its phase of maximum climate habitability. Initially positioned at 1.8 AU from the red giant sun, orbit expanded by 15% solar mass loss, the planet will receive about 45 to 50 times more energy than Earth receives today, bringing average surface temperature to 104 degrees Fahrenheit or 40 degrees Celsius, with summer equatorial peaks of 140 degrees Fahrenheit or 60 degrees Celsius, and summer polar temperatures of 77 degrees Fahrenheit or 25 degrees Celsius. Martian permafrost will completely melt in a few million years. Released water, estimated at about 100 million billion tons, will temporarily form global oceans 50 to 200 meters deep. The atmosphere will dramatically thicken to 500 to 1,000 millibars due to polar cap sublimation and CO2 release from soil, creating a greenhouse effect that will stabilize the climate. This will truly be the golden age of Mars. Subtropical temperatures, liquid oceans, an atmosphere dense enough to protect from radiation, and abundant water availability. For 200 to 300 million years, Mars will probably be more habitable than primordial Earth ever was. it'll be the perfect time for our extremely distant descendants to permanently relocate to the red planet. 7.3 billion years, the Sun at maximum expansion. The Sun will reach its maximum size as a red giant, 200 to 256 solar radii, with brightness 2,000 to 3,000 times current levels, and surface temperature around 5,940 degrees Fahrenheit or 3,300 degrees Celsius. To give an idea of the dimensions, the expanding solar globe would exceed even Earth's orbit. Outer planets. Europa becomes a new ocean world. Europa will experience its most spectacular transformation. Europa's subsurface ocean, finally freed from its 20-kilometer thick ice crust, will emerge as an exposed global ocean 60 to 100 kilometers deep. Ocean temperature will reach 59 degrees Fahrenheit or 15 degrees Celsius, perfect for complex life forms that might have evolved in darkness for billions of years. Hydrothermal activity on the ocean floor will intensify by a factor of 10 to 20, creating an energetically rich ecosystem that could support a surprisingly complex biosphere. It'll be as if Europa transforms from an ice ball into a true ocean world, with waves, storms, and perhaps even marine life that can finally see sunlight for the first time in solar system history. But the real protagonist of this era will be Titan, which will become humanity's final destination during the Sun's red giant phase. Titan's transformation will be absolutely spectacular. Surface temperature will rise from minus 290 degrees Fahrenheit to 32 degrees Fahrenheit, or minus 179 to 0 degrees Celsius, causing complete evaporation of methane and ethane lakes that characterize its landscape today. The nitrogen atmosphere will thicken, creating a greenhouse effect that brings surface temperature to 68 degrees Fahrenheit or 20 degrees Celsius. Surface water ice will begin melting, forming the first liquid water oceans in Titan's history. This phase will represent Titan's moment of maximum habitability, optimal surface temperature for humans, a dense atmosphere that will protect from cosmic radiation, liquid water availability, and rich organic chemistry developed over previous billions of years. 7.6 billion years, the most violent phase. After 600 million years as a red giant, the Sun will experience the most violent moment of its entire existence. The solar core will reach critical density of 1 million grams per cubic centimeter and the incredible temperature of 180 million degrees Fahrenheit or 100 million degrees Celsius. At this point, something extraordinary will happen. Degenerate helium will explosively ignite through the triple alpha process, a nuclear reaction that converts 3 helium-4 nuclei into carbon-12. Released energy will equal 100 billion joules, an amount of energy equal to 100 billion times current solar brightness, concentrated in a few terrifying minutes. It's as if the Sun suddenly became a star-sized nuclear bomb. Fortunately for surviving planets, this energy remains trapped within the massive stellar envelope and isn't directly observed from outside. The cosmic nuclear winter. What happens next is equally dramatic. The Sun will rapidly contract from 200 to 10 solar radii in less than a million years, assuming a yellow-orange color. Surviving planets will experience brutal and sudden cooling. Solar brightness will collapse from 2,000 to just 50 times current levels, causing a cosmic nuclear winter lasting 10 million years. It's as if someone suddenly drastically lowered the thermostat of the entire solar system. Mars will rapidly return to hot desert conditions, with temporary oceans refreezing in a few centuries, though temperatures will remain higher than current ones. Europa will see its exposed ocean freeze again, reforming an ice crust 30 to 40 kilometers thick in just 100,000 years. Titan will return to its original atmosphere, with methane recondensing to form the surface lakes that characterize the satellite in remote epochs. At this point, Triton will represent our last habitable frontier. This large moon of Neptune, with its 2,706 kilometer diameter, will be in the optimal habitable zone during the final phases of the red giant. Humanity's strategic migration will follow this fascinating sequence: Earth to Mars, Mars to Titan, Titan to Triton, accompanying the expansion of the solar habitable zone over at least 1 billion years. 8 billion years, the second red giant phase. After 130 million years of relative stability, the Sun will experience its final spectacular transformation. Core helium will be completely exhausted, leaving a carbon-oxygen core surrounded by concentric fusion shells. It's like a cosmic onion with different nuclear reaction layers burning at different temperatures and rates. The Sun will enter what astronomers call the asymptotic giant branch, a phase characterized by dramatic thermal pulses every 1,000 to 10,000 years, causing incredible brightness variations between 1,000 and 5,000 times current solar levels. Imagine living on a planet where every 10,000 years or so, the Sun suddenly becomes 1,000 times brighter for several centuries. During this final phase, the Sun will lose mass at an impressive rate of 100,000 billion tons per year, carrying away 30 to 40% of its original mass in just 20 to 30 million years. It's as if the star is literally evaporating into space, blowing itself away with an increasingly intense stellar wind. 8 billion years, the planetary nebula. The final phase of the giant will culminate in a series of catastrophic expulsions, during which the Sun will completely eject its outer layers in 4 to 6 explosive events, each separated by about 100,000 years. It's as if the star is literally stripping off its cosmic clothes, layer by layer. The final stellar wind will reach speeds of 1,243 miles per hour, sweeping away the last remnants of the solar atmosphere and finally revealing the incandescent stellar core, a white protostar with surface temperature of 360,032 degrees Fahrenheit or 200,000 degrees Celsius. The resulting planetary nebula will extend 2 to 3 light years, illuminated like cosmic neon by ultraviolet radiation from the central core. Expelled gases rich in carbon, nitrogen, and oxygen created during previous phases will form complex structures of indescribable beauty. Multicolored concentric rings, brilliant density nodes, and polar jets extending trillions of kilometers. It'll be like a giant cosmic firework lasting tens of thousands of years. The few planets surviving this final phase will experience ultraviolet radiation bombardment 1,000 times greater than current levels. Any residual planetary atmospheres will be ionized and dispersed into space, while rocky surfaces undergo deep chemical alterations. Mars, now positioned 3.1 AU or 288 million miles from the stellar core, will receive UV flux that definitively sterilizes any residual biological traces, transforming the surface into a desert of vitrified regolith that will glow under ultraviolet light from the dying sun. When the spectacular planetary nebula dissolves after 50,000 years, only the exposed stellar core will remain, a white dwarf with 0.6 times the original Sun's mass, but compressed into Earth-sized volume. Density will be 1 ton per cubic centimeter, so extreme that a simple teaspoon of this material would weigh as much as a car. Its matter in such an exotic state it defies our imagination. During this period, planetary orbits will finally stabilize at their definitive positions. Mars at 3.1 AU or 288 million miles, Jupiter at 9.5 AU, Saturn at 17 AU. Surface temperatures will stabilize at their final, incredibly cold values. Mars minus 328 degrees Fahrenheit or minus 200 degrees Celsius, similar to Pluto today. Jupiter minus 382 degrees Fahrenheit or minus 230 degrees Celsius. Saturn minus 400 degrees Fahrenheit or minus 240 degrees Celsius. Uranus and Neptune minus 418 degrees Fahrenheit or minus 250 degrees Celsius. The long cosmic sleep. After billions more years of gradual cooling, the white dwarf will have cooled to 10,832 degrees Fahrenheit or 6,000 degrees Celsius, similar to current Sun surface temperature but with reddish color due to its reduced size. Brightness will have dropped to 1/10,000th of today's Sun, making the star practically invisible even from distances of a few light years. The solar system will be immersed in profound and definitive cosmic silence. Surviving planets will orbit in complete darkness, illuminated only by the white dwarf's faint reddish light that will seem little more than a very bright star in the night sky. There will be no more auroras, no more seasons, no more life as we know it, only silent movement of dead worlds through frigid space. Surviving planets will share similar and extraordinary fates. While their orbits gradually decay through gravitational wave emission, taking 10 to the power 15 to 10 to the power of 18 years to slowly spiral toward the white dwarf, the very matter they're composed of might eventually completely dissolve into photon and neutrino radiation, leaving behind only pure energy dispersing in the expanding universe. 100 billion years, the black dwarf phase. When the white dwarf temperature reaches near absolute zero, then all outward radiation ceases, and what was once our sun will become a black dwarf, an extinguished ember the size of Earth, absolutely unobservable. Reaching this phase has never been observed in any star, since the process requires time longer than the universe's age. And here we're literally beyond any human comprehension capacity. What remains is the consolation of knowing that for us Earthlings, if we want and if we can, there will be the possibility of extending our survival for at least 1 billion years by migrating to increasingly outer planets and moons. We, obviously, won't be there.